Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last lecture, we started discussing about one approximate method using which we can solve difficult quantum mechanical problems. The method that we have been discussing is the variational principle. In today's lecture, we will look at one particular application of variational principle and we will see how we can use them to describe chemical bonding. Just to remind you, in variational principle, we discussed that if we have a system whose Hamiltonian is not exactly solvable, that means we do not know the true ground state wave function psi 0, nor do we know the exact ground state energy E 0 corresponding to this Hamiltonian. In such a case, we can define a trial function or a guess function phi using which we can evaluate this energy using this expression. What variational principle guarantees us is that this energy that we obtain by with respect to the trial function E phi is always going to be greater than or at the best going to be equal to the true ground state energy E 0. So, that means this E phi, no matter what trial function we decide to use, the corresponding energy is always going to be greater than the true energy. In that case, what we can do is that we would say that the limit with which if E phi approaches E 0, that means the trial the energy corresponding to the trial function when it approaches the ground state energy E 0, then the wave function, the trial function phi would also approach the true ground state function. Technically, how do we do that? We defined phi, the trial function, by defining a variable alpha within this phi, our trial function, and we therefore, when you obtain E phi, all other variables would go away because we are integrating them with respect to all the coordinates. So, therefore, the energy E phi will be a function of alpha. Now, since variational principle tells that this E phi is always going to be greater than E 0, so therefore, we can try to find out what is the minimum possible value of E phi, and we do that by minimizing this E phi, which is now a function of alpha with respect to alpha. When you do that, you would find that for a given value of alpha, this relation will hold true. Now, for that value of alpha which minimizes E phi, we call that alpha m or alpha minimum. We use this value of alpha to describe this phi, the trial function, and this function phi of alpha m is actually the best description of the wave function given the choice of the trial function that we have made. Similarly, when you plug in alpha m in the expression of energy E phi, that energy is actually the best case scenario for the energy description for the ground state energy given the choice of phi we have made. So, on the basis of our choice of the trial function, we can get the best possible wave function and best possible energy value that would describe the quantum mechanical problem, which is not exactly solvable. We discussed another approach to do this variational principle. In this case, we defined our trial function as a linear combination of several functions. So, we defined our phi as sum of Ci psi i's, where psi i's are some known functions. We can of course choose psi I as one of the eigenfunctions of a complete set which we can get as an eigenfunction set of eigenfunctions of a Hermitian operator, or we can choose any number of functions psi i's and define our trial function as a linear combination of them. Under this definition, the trial wave function, we know the psi i's. So, therefore, only thing that is not known are these Ci's. So, in the wave function, if we get the Ci's, the coefficients, then we actually know the trial function. So, therefore, we have to find out the best possible values of Ci. We saw that when we use this definition of phi into this energy expression, we obtain a relation which gave us that we have to, if our trial function has n number of functions, then we ended up in a situation where we have to solve this n by n secular determinant, or we have n number of linear equations. So, that we have to solve. In other words, what we have to do for when we are taking trial function as a linear combination of function, we have to construct this n by n matrix and then diagonalize this, because this solution is essentially diagonalizing this matrix. Once we diagonalize them, the eigenvalues would represent the energies, the eigenvectors would represent the coefficients C 1, C 2 and to C n. So, once we construct this matrix and diagonalize them, our energies and Ci's are there, and once we have Ci's, of course, we have the best possible description of the wave function given the choice of starting functions we have made. What we do today is that we will use this method, this when we are using defining a trial function as a linear combination of several functions, this variational approach is called linear variational approach. So, we would use this linear variational approach to solve one problem, and this problem is the quantum mechanical solution of hydrogen molecule. This is the Hamiltonian of hydrogen molecule that we know. So, the treatment that we are going to do for the hydrogen molecule, the method that we are going to use is also known as valence bond treatment of hydrogen. We will slowly discuss about different approximations of this approach. So, this is what the Hamiltonian is. The first term is the kinetic energy of the nuclei. So, since I have hydrogen molecule, there are two hydrogen nuclei. So, these are the kinetic energy operators of the nuclei. Then you see these are the kinetic energy operator corresponding to the electrons. Again I have 2 electrons. So, therefore, small I goes from 1 to 2, and I have 2 kinetic energy operators corresponding to the electrons, and then each electron, now I have 2 electrons, each electron will interact with each of the nucleus. So, I have 2 nuclei and I have 2 electrons. So, therefore, when you look at for I equals 1 to 2, I have A equals goes from 1 to 2. So, therefore, this term shows electron nuclear attraction. So, together I would have 4 such terms, plus I have electron repulsion and I have nuclear repulsion. Within Born-Oppenheimer approximation, we can ignore the kinetic energy of the nuclei. That means, we say that we are going to look at the electronic part of the Hamiltonian by fixing the 2 hydrogen nuclei at a certain value of capital R, which is the nuclear distance. When we do that, the kinetic energy operator becomes 0 and the potential energy corresponding to the nuclear repulsion becomes a constant. And when I look at these terms over here, I have some 1 electron operators. These are 1 electron operators, and the electron repulsion is a 2 electron operator. So, let us write down only the electronic part of the Hamiltonian, and we see that we will have the Laplacian is corresponding to electron 1 is given by as nabla 1 square. So, this is the kinetic energy of corresponding to electron 1. This is potential energy between electron bond and 1 and nucleus A. This is the kinetic energy corresponding to the electron 2, and this term is the potential energy between electron 2 and the nucleus P. So, we are saying that when we have hydrogen molecule, so we have hydrogen, we call this A and B. So, we have 2 nuclei A and B and 1 electron on each hydrogen. So, and then we have, when we expand this, then we have terms like 1 R 1 B minus please note we are writing this Hamiltonian in atomic units. So, therefore, mass of electron is 1, h bar is 1, 4 pi epsilon 0 is 1 and charge of electron is 1. So, that is why we have this simple expression for the Hamiltonian operator. So, now this is the total electronic Hamiltonian that we have. Mind you, this is a constant. Look at these first 2 terms. you see that these first two terms together, they express that this is the kinetic energy of electron 1 and this is potential energy of attraction between electron 1 and nucleus A. So, if I call this electron of nucleus A as 1 and I call this electron of nucleus B as 2, you see the first two terms actually represent the case of one hydrogen atom, and let us call this hydrogen atom as Ha. So, this is the Hamiltonian corresponding to one hydrogen atom. Similarly, you see this term, the kinetic energy operator corresponding to electron 2 and the potential energy attraction between electron 2 and nucleus B. So, these two terms together are the Hamiltonian corresponding to hydrogen atom B. Now, when hydrogen atom A and hydrogen atom B are far away from each other, so that means we have simply two hydrogen atoms, these two terms describe the Hamiltonian of the system. But when I bring them together, bring them closer, of course, electron 1 which was in hydrogen atom A would also start interacting with the nucleus of B hydrogen. Similarly, electron 2 would start interacting with the nucleus of A hydrogen atom. So, these two expressions are given in this way R1b, that means interaction between electron 1 with nucleus B and interaction of electron 2 with nucleus A. And similarly, when you bring two hydrogen atoms together, the two electrons will start repelling each other. So, therefore, plus 1 over R12, and similarly when you bring two nuclei together, there will be a nuclear repulsion term. So, we see that these terms are 0 when the two hydrogen atoms are far away from each other. Once we bring them closer, that means once we are coming to make a bond between them, these operators start appearing. So, therefore, the hydrogen molecule is in a sense two effective hydrogen atoms. So, if I have to consider only this part of the Hamiltonian, let me call this Ha. I know this is one hydrogen atom and I know its ground state functions. Let me call this as 1s A is the ground state wave function, ground state eigen function corresponding to hydrogen A, and I give this electron 1 index. So, because electron 1 is there. So, this becomes an eigen function of this Hamiltonian which corresponds to the hydrogen atom A. Now, if this is the ground state eigen function, the corresponding energy is, we know that the energy of the ground state of hydrogen atom is minus 0.5 atomic unit, since we have written down the Hamiltonian in atomic unit. So, therefore, the energy also we are writing in atomic unit multiplied by the function itself, because this is an eigen function. So, this Schrodinger equation we have solved for hydrogen atom A. Similarly, we can write down corresponding to the B nucleus. So, where for B nucleus I will define the ground state function 1sb holding electron 2, the energy will be same minus 0.5, and since this is an eigen function, so I have this. So, these two equations I know, in fact, I know 1sb2, 1sa1 because I have solved the hydrogen atom problem exactly. Now, but we are not solving hydrogen atom problem, we are solving hydrogen molecule problem. So, now what we would see is that, okay, fine, let us say that since hydrogen molecule is in a sense that we are combining two hydrogen atoms. So, let us define our eigen function or a state function, or so to say a trial function for the hydrogen molecule as product of these two eigen functions. So, I call this 1sa1, 1sb2. So, this function I know, this function I know, because I can solve independently the hydrogen atom. So, what I am defining is that let my guess function be a product of these two functions. This is this is a way to describe my trial function, but I see a problem here. The thing is that I have defined this electron 1 with the nucleus A, electron 2 for nucleus B. That is all right as long as we say that two hydrogen atoms do not know each other, but the moment they start interacting with each other, which is happening because we are discussing about hydrogen molecule. So, once the molecule is formed, there should be the electrons should not be distinguishable. So, the indistinguishability of the electrons has to be preserved. So, that means what I should do is that I should say that I would not know whether electron 1 after the hydrogen molecule is formed, I would not be able to tell you whether electron 1 is from hydrogen A or electron 2 is from hydrogen A, because the electrons are indistinguishable in a molecule. So, therefore, to incorporate indistinguishability of the electron, let us define another way. So, if I say that okay, 1s A orbital takes electron 2 and 1s B orbital takes electron number 1. So, if I express this way the trial wave function, then I see that 1s A is now holding electron number 2 and 1s B is holding electron number 1. So, let us call this psi 1 and this psi 2. So, now I have two different ways of writing, and to make sure that the electrons are indistinguishable, I simply call this phi as some linear combination of psi 1 and psi 2. So, I define my trial function phi as linear combination of two functions psi 1 and psi 2, where psi 1 is the product of two known functions, psi 2 is also product of two known functions. So, in this case the trial function phi is sum of two functions where psi 1 and psi 2 are in principle known. What is not known is C 1 and C 2. So, now we have come to a situation where our trial function is a linear combination of two functions, and we know that when this is the case, when our trial function is a linear combination of two functions, then all we have to do is that we have to look for this solving this secular determinant. So, that means we have to construct this 2 by 2 matrix y 2 by 2, because my trial function is linear combination of two functions. So, therefore, the matrix that I would have will be a 2 by 2 matrix. If I had expressed my trial function as a linear combination of 3 or 4 or 5 functions, then I would have to solve the 3 by 3 or 4 by 4 or 5 by 5 secular determinant, but in this case I have this 2 by 2 matrix to look at. So, if you remember, we have defined this H11 as the energy integral, S11s are the overlap integrals, and what are, so now we would spend some time in discussing what are the values of these integrals H11, S11, and we have this E which are unknown. Once we diagonalize this Hamiltonian, we will see that the E's the eigenvalues will be the energy, the C1 and C2 will be the coefficients. So, let us see first look at the overlap integrals or the S integrals. In particular, we will first discuss about S11. When we look at S11, if you remember, S11 is the overlap integral of psi 1 with itself. So, now when you look at psi 1 is given by this expression. So, now I have to evaluate this integral. So, let us try to do that. So, I see so this is my psi star and psi 1 star, and then psi 1 will be simply the function without the complex conjugates, and I have to integrate over dr1 and dr2. r1 is the coordinate corresponding to electron 1 and r2 is the coordinate corresponding to electron 2. So, I am integrating it over all electron space. Now, when I see this, I see that I have some terms which depend on electron number 1 and some terms which depend on electron number 2, and since I am integrating over dr1 and dr2, so therefore, let us separate the terms that have electron number 1 dependence and write the terms that have dependence in electron number 2 separately. When I do that, I see that the first term has only electron number 1, the second term has only electron number 2 dependence. Let us look at the first term. What do I see? I see that this is an overlap of 1s A orbital with its own complex conjugate. Now, what is 1s A? 1s A is the ground state eigenfunction of hydrogen atom hydrogen atom that we called A. So, this eigenfunction, these functions are eigenfunctions of a Hermitian operator corresponding to the Hamiltonian of hydrogen atom A. Since they are Hermitian eigenfunctions of Hermitian operator, they are orthonormal. So, therefore, they are normalized function. So, therefore, their value becomes becomes 1. What about this term? This is again 1sb is the eigenfunction corresponding to the hydrogen atom B. So, therefore, they are also individually normalized. So, therefore, this overlap also is 1. So, therefore, I get my S11 as simple 1. So, this term comes out to be 1, and similarly you should try to show that S22 would also come out as 1. Now, let us now look at the overlap integral S12. What is S12? This is the overlap of psi 1 with psi 2. So, that means psi 1 in the bra, psi 2 in the cat. So, psi 1 star psi 2. So, psi 1 is given here, psi 2 is given here. Let us write this down. Psi 1 star is 1 SA star 1, 1 SB 2. So, both are complex conjugate. Psi 2 is obtained by exchanging the electrons, and I have to integrate this over dr1 and dr2, the space of electron 1 and electron 2. So, since again similar to what we did here, we have to separate the terms which have direct dependence on electron 1. So, let us do that. So, I see this term and this term have electron 1 dependence. So, I integrate them over dr1, and I have these two terms having dependence on electron 2. So, I collect them. Now, I have this term. Now, let us look at these two integrals. So, the first one depends on only on R1, the second term depends on only on R2. Now, let us look at this function. What is the value of this? What does it tell me? This tells me the overlap of 1SA and 1SB. So, 1SA and 1SB are two different functions. Often students get confused and say that okay, they are going to be orthonormal and orthogonal. So, therefore, this value is 0, but mind you, this 1SA is an eigenfunction of a Hermitian operator corresponding to Hamiltonian A. 1SB is an eigenfunction of a Hermitian operator corresponding to the Hamiltonian of hydrogen B. 1SA and 1SB are not eigenfunction of the same Hamiltonian. They are in fact the eigenfunctions of two different Hamiltonians. So, therefore, even if the two different the Hamiltonians are individually Hermitian, there is nothing that we know to tell that that 1SA and 1SB would actually be orthogonal to each other. So, therefore, this is not going to be 0, this will have some finite value. Let us call this finite value as S. We will come back to this value of S, and similarly when you look at this 1SA and 1SB, they are again not orthogonal to each other, rather their overlap will be some finite value, and since I have S multiplied by S, I call this S square. Now, see, let us look at what is this overlap function S. Now, this overlap is 1SA holding electron 1 and 1SB. Now, let us see if what is 1SA? 1SA is the eigenfunction of hydrogen atom A. So, if hydrogen atom A is over here, so 1SA orbital, since you know that it has functional dependence of e to the power minus z divided by r, z by A into r. So, you have essentially e to the power minus r type of term. So, if this is my hydrogen atom A, the nucleus, the wave function 1s would look like this. Similarly, if my hydrogen atom B is here, the 1sb would look like this. So, I have at the nuclear position, this has maximum amplitude, and then it falls on both sides as a function of e to the power minus r. Now, I see the overlap is simply the overlap between the two functions. When these two hydrogen atoms are far away from each other, as it is shown here, the overlap between them is going to be 0, because there is no overlap between them. But when I bring the hydrogen atom B closer to hydrogen atom A, that is what I do when I define a bond, for example. So, suppose now this hydrogen atom B is approaching hydrogen atom A, and now my hydrogen atom B is shown here. So, if I draw the wave function, one is eigenfunction of one B nucleus, then it would look like this. Now, you see that the two wave functions, they started overlapping. So, the overlap, this S, the overlap integral, will be a function of the internuclear distance. So, if the distance is very large, so if I have to draw S as a function of r, where capital R is the internuclear distance, of course, when r is very large, that means the two hydrogen atoms are far away from each other, the overlap integral will become 0, and when they come very close to each other, it will have a larger value. So, then if I have to see, I have to plot S of r, this would be a function of which will look like this. So, now we see that the overlap function S square is actually S of r square. So, this is a function, the overlap integral is going to be a function of internuclear distance. So, we see that S11 becomes 1, S22 becomes 1, S12 is what we obtained as S square, where S is simply the overlap of 1s A and 1s B orbital. And similarly, you can show this is also going to be same as S of S21. So, this value. So, in today's class what we have done is that we have formulated the hydrogen molecules Hamiltonian, and we are trying to solve this using variational principle, and we have defined our guess function as a linear combination of two functions psi 1 and psi 2. Please note, psi 1 and psi 2 are different from each other by the fact that we have simply exchanged the two electrons. In psi 1, electron 1 was with nucleus A, electron 2 was with nucleus B, but we have defined psi 2 where it has electron 2 with nucleus A and electron 1 with nucleus B. We have done this exchange and we have defined a trial function phi as a linear combination of C1 psi 1, linear combination of psi 1 and psi 2 as C1 psi 1 and C plus C1 C2 psi 2. This way of describing the trial function as a linear combination of functions where we have obtained this function by exchanging the electron is known as the valence bond treatment. So, in today's class we saw what are the overlap integrals. We still have to look for the energy integrals, because these H11, H21 or H12, these quantities are not yet known. That is what we will discuss in our next class, that how we will get these energy integrals, and once we have the energy integrals we can solve this secular determinant and then find the eigenvalues and eigenfunctions corresponding to the hydrogen molecule. But the solution that would come from this treatment is based on the approximation or the trial function phi that we have defined by exchanging the electrons between the two nuclei, and this treatment is known as valence bond treatment. What are the solutions of this valence bond treatment? The eigenfunctions, the eigenvalues will be the topic of discussion in our next class. Thank you for your attention.